Seeking English S.A.T. Workbook, page 465, problem 1. The answer to this is in the book, and there is also an explanation of this problem in the book. So I'm going to try to give you a little bit more, or something different from what's in the book, just to make sure that you squeeze a little extra value out of this problem. It says a certain radioactive substance decays at an annual rate of 8%. If the current amount of the substance is 750 milligrams, which of the following expressions represents the amount of the substance remaining after T years? So if you look at your answers, you see the expression for T years here is the same for all 4 answers. So that's the good news. Okay. The way that the way that T is notated is not especially confusing. This is oddly an opportunity for me to go over again what I've already mentioned in terms of taxes and discounts. But teacher, this doesn't have anything to do with money. This is radioactive decay. I know, and I mentioned when I did problems that actually involved taxation and discount. I think I mentioned that we were going to be talking later about radioactive decay, so we're doing that this time. Now, if the amount of the substance is increasing, that is more like, mathematically, it is more like taxation. If it is decreasing, that is more like a discount. So I'm going to talk about radioactive decay as if it's a discount on the amount of radioactive material. How does this work? Well, let's go back and look at this again. I make all my students look at this at least twice, and often many times more than twice. I know I keep mentioning the glare. I'm going to not mention this sometime. I'm going to keep mentioning it. Okay, so with tax and discount, again, people are not very confused about tax. They know that it makes a positive number larger if you multiply something by something. If you multiply something by a number that is larger than 1, it becomes larger. People are often confused about discount, and it's even more confusing when it's not actually money and when it's radioactive decay. Is that it makes things smaller, we know that, but people think of discount as being a subtraction process or a division process. It's not really what it is. What you have to do is take a positive number, multiply it by something that is smaller than 1, and it will become smaller. Okay? So the way we get a multiple to calculate a taxed version of something is we take 1 and we add tax to it. Okay, and that seems obvious. Okay, so in this case, it would be, if we're getting larger in some alternate universe, 8%, the multiple would be 1.08. Okay, that would be our multiple if we're getting the amount of the material we're increasing every year. Okay, in the actual problem, which is similar to our universe, we take 1 and we subtract the discount from it. Okay. So instead of adding this 8% to 1, we subtract 8%, 0.8 from 1, and we get 0.92. That should be our discount multiple. So if you don't see 0.92 or the equivalent in the answers, there's something wrong. So that is to say, if you see answers that don't include that, or don't include the equivalent in some way, those are probably bad answers. Do we see 0.92 at all? Yeah, we see it here, and we see it here. And at this point, we can begin talking about more broadly what's wrong with these answers. In this case, this is the base amount of material, and it is multiplied annually by the rate of decay. So it's going to shrink down to 0.8% of itself in the first year, and in the second year, 0.8, it's going to be practically gone. 750 milligrams. Well, if it's plutonium, you can keep worrying about it basically forever. Otherwise, it's going to be gone pretty soon. This one, 750, is the correct amount of material, and it's multiplied by our discount multiple, which is slightly smaller than 1. Okay, annually. So that's probably the correct answer. Let's not commit to that till we see whether maybe there's a better answer. This one has the decay rate as the base amount of material, which is wrong. Okay, and it is multiplied by 750, annually. So even though this starts at a very small amount of material, it's gonna get really large as you go on. Okay, these in both these cases, your multiplier is making the thing larger, not smaller every year. It's getting huge, huge very quickly. It wouldn't even matter whether the base rate, whether the base amount is correct or incorrect, or whether it's larger than one or smaller than one. The operation that you're performing in both these cases is incorrect because the multiplier is larger than one, and it will make the material grow in size rather than shrink. In this case, in these cases, it's getting smaller because your multiplier is smaller than one. Okay, but in one case, it is coming down to a tiny fraction of its original. And I know, hypothetically, there's substances that will do that. We're not talking about those. We're talking about one that becomes smaller by 8% annually. It becomes a little bit smaller every year. That's this answer here. So again, the slightly different explanation is in the book, but I wanted to show you this again because this is a useful way of conceptualizing things that don't always strictly involve money. Again, why do I use it? Well, not everyone has had firsthand experience with radioactive decay, or if they have, they haven't known it. Most people have paid a tax and not liked it. Most people have received a discount and they have liked it. So we have an investment. Our brain is already invested in taxation and discount processes. So if you can apply an understanding of how that works with money to things that are not money, it may help you on the real test.